Hello, this is Mr. Huff, and we're going to talk about tolerances. This is also in Unit 7 of my PLTW. The key idea with tolerances is that variation when you're manufacturing parts is not avoidable. So if you want to have something that has interchangeable parts, you need to understand the specification limits. How small can it be and how large can it be? And still be a functional part for whatever you're building. If your tolerances are too large, it may affect the function of the part. And then you've all bought those cheap pins that look like a big pin, but they're not a big pin. And sometimes the little pin that goes into the tube that holds the pin together, it's too large, or they're too tight, and the barrel cracks. And sometimes it's too large, they're not close enough together, so the little pin part tends to slip out and fall out. Small tolerances make sure things work better. The quality is higher with a lower tolerance. But as you keep reducing that tolerance, it makes it more difficult to manufacture. And if you keep pushing it down, it can make it very, very expensive, and it requires a lot more measurement and inspection. So you want to use the highest tolerance you can that still produces a quality part. So this takes some thought and some experiment. ANSI standards basically say everything's going to have a tolerance. A lot of times with the drawings we'll produce, we'll specify the tolerance for all measurements with the noted exceptions. So another way of saying it is a tolerance is an acceptable amount of dimensional variation that will still allow an object to function correctly. So there's three kinds of tolerances. Let's take a look at those. And you can see the little diagram on the right has some examples. Okay. You have limit dimensions. So this is a specification that says it can be no more, let me go back. Limit dimensions, in this case, you can't go above 9.8 or below 9.75. So that measurement has to be in between those two numbers. You have bilateral tolerance. So in this case, you're shooting for a diameter of 1.17, but it can go 0.002 inches above or below that central measurement. So what you're trying to do is hit that 1.170 measurement, but you can go above it a little bit or below it a little bit. It makes a window. And then you have a unilateral tolerance, which says it has to be 0.5. It cannot be smaller than 0.5, but it can be greater by 0.005. So it's like having a threshold on one side that lets you go above and below, but the other one you can't go beyond the measurement that you're targeting. So those are the three kinds: limit, bilateral, and unilateral. Most of the tolerances we will use are bilateral. And then it explains limit dimensions a little more. So we have limit dimensions, so it can be between these two numbers. So any number between those is allowed. Bilateral, plus or minus 0.03, plus or minus 0.05. It's an equal amount of variation on either side of a target. We designate that with a plus or minus. Okay, that's all for that. Unilateral. This says you can go above 0.5, but no more. You can't go below 0.5. So it's a variation only in one direction. So you have separate values for plus and minus. And then there's an exercise on here about identifying the kind of limits that are applied. So there we have unilateral, here we have bilateral, and here we have limit. So this is the specified dimension. This is what Inventor will default to when you put the measurement in. So what this says is it can be plus or minus 0.05, which means we have an upper limit of 1.55 and a lower limit of 1.45. And this again is explaining tolerance. So to calculate tolerance, you just start with the defined or the specified dimension, and then you add and subtract the limits. In general, the customary application of tolerance is as follows. For an angle, that means it's plus or minus 0.5 degrees. So 1 degree plus or minus a half a degree. For linear dimensions that only have one decimal place, the customary expectation is that that would be plus or minus 0.2 inches from that, not 0.2, 0.02. So you can see we are going to be at, let's say this is 1.1, and that means it could go as high as 1.12 or as low as 1.08 and still be in that tolerance. For 2 decimal places, you permit as much as a 0.01, and for 3 decimal places, as much as a 0.005, or with 3 decimal places there. So that's how the limits are generally defined. If they're not specified, that's what you can expect. Okay, so a lot of times what we'll do on a drawing is we'll have a little table like this at the bottom that will say if it's this precision, then this is the amount, this is the set tolerance for everything, and then any exceptions are noted. So this number has 2 decimal places, so it's going to be plus or minus 0.01. In that last decimal place, it can go up or down by 1. And it shows you that. So that's how you would read that. So most of the time, you just type up this little table somewhere on your drawing as text and run with it from there. Another thing to keep in mind is when you put a tolerance specification on a drawing, if you're manufacturing that part and it is not inside those tolerances, that dimension doesn't fit, even though you've made the whole part and it's only one measurement that's wrong, you throw the whole part away, or downgrade it or whatever, and get rid of that because it's out of spec and you can't use it. So this is why when you make that tolerance tighter and tighter, reducing that limit to a smaller and smaller number, it gets more and more expensive to make that part and more difficult to make that part. All right, there's 3 types of fit when things fit together. We have clearance fit, interference fit, and transition fit. So let's take a look at these a little more. Okay, a clearance fit is this. In this case, you have a plate with a hole in it, and then you have a shaft that's going to go in that hole. And in this case, the dimensions are set such that the largest dimension of the shaft and the smallest dimension of the hole will always allow the shaft to slide through the hole, because the hole is always going to be larger than the shaft, so the shaft will pass easily through that hole. Okay. The next thing is an interference fit, and if you look at this, the smallest this can be is 9.92, and the largest this one can be is 9.90. And this shaft is intended to go into this hole, but what it's going to do is they're going to interfere with one another. That means you have to put these 2 parts together with a press, and it's going to hold the shaft in place by compression, because the shaft is always going to be larger, just very slightly larger than the hole it goes into. Think about a Bic pen. It has an interference fit. That's how the pen stays in the barrel. You push the pen part up into the barrel and it stays put together because of an interference fit. That pen part is a little bit larger than the hole that it goes into, and you press them together. Okay, there's another idea called the maximum material condition, and this is defining the largest amount of material. So in the case of a linear dimension, it's the upper limit of your dimension. And when you're talking about a hole, it is the lowest dimension, the lowest diameter of the hole. So it's like the total length it could be, or the smallest hole you could have. The smaller the hole, the more material you have. So the maximum material condition. You also have LMC, which is the least material condition. In a linear measurement, this is the lowest measurement possible because that's going to produce the least amount of material. And for a hole, it's going to be the maximum diameter of the hole because that's removing material, so that's going to make the lowest amount of material when you talk about a hole. So allowance is talking about the minimum clearance between or maximum interference between parts. So you're thinking about how parts are clearing or how they're interfering with each other. So that's why we need to understand MMC and LMC. Okay, so they have an example of calculating the allowance here. So let's just page through this until it's all here. So let's take I'll give you a moment to look at the slide here and go read these. So you might want to press pause right here to absorb that. And again, take a moment to pause this to make sure you understand the MMC, the maximum material there. So, okay, to wrap it up, in general, the more significant figures in the dimension, the tighter the tolerance. That means it's also more difficult to manufacture, and it's going to be more expensive to manufacture. Overly precise dimensions and overly tight tolerances are going to run your cost up, and you need to specify your dimensions only to the precision and tolerance necessary for the part to function properly. So you want to identify those the values that are required so that you don't run the cost up unnecessarily. So if you're building something for, let's say, a desk in a home for a person to use, the tolerances are not going to be real tight. But if you're building something like a satellite or a spacesuit where leakage of gas is really important, then you're going to have extremely tight tolerances. So that's all we have to say about tolerances.